keep you in touch as Explore Scientific is. Hey Ken, how are things going out there? You're in Valentine, Nebraska at this time. Is that
That,
where you are?
that's correct. I'm in Valentine. We came into town here at Reservoir. Uh, there's a class this afternoon from 2 to 4 at Valentine High School.
Right.
And
And
so
of
I'm
course, we're talking about the Nebraska Star Party. So, but it got kicked off today. Is that right?
actually started off last night sort of with a welcome ceremony, and it was cloudy. So everybody
Mm.
just sort of sat around. It rained about, I don't know, 1 o'clock in the morning, a little bit. And it's clearing off right now. I'm going to go set up. I'm going to get some lunch, and I'm going to go set up at Valentine High School and
Okay.
have 82 millimeter giant binoculars out there for people to look at the sun with.
Sure. That
It's
sounds
a really
great.
nice spot, so people will love that. And I got some other stuff I'm going to set up.
Very cool. Yeah.
Yep.
So I got a message back from John Johnson, who is one of the guys that heads up Nebraska Star Party, and he says there's pretty nice turnout already. How many people have already shown up?
How many people there? My wife is sitting here with me. What, 100
I'd
people?
say probably 100 people.
Probably 100 people were there
100
last
people
night.
or so? Okay.
Thank
All
you.
right. And I know more are coming, so they
Yeah,
come as
there's
it gets closer to the weekend.
correct. There's supposed to be like 300 registered, I think. So it's going to be a pretty good sized event if they all show up. And was just looking at the forecast and talking to a guy we ran into that we talked to last night. He said tomorrow night looks like it's going to be a really good night. Then Thursday and Friday are going to be good.
Yeah.
So I'm going to get 2 or 3 nights of good viewing in, and it's Merritt Reservoir is what, 30 miles south of west of Valentine, and
Yeah.
about 50 miles north of a little town called Mullen, and there's just no light pollution out
It's
there.
dark out there. I know. I know. That's great. Weather, is it hot or is it how's the temperature?
It's 77 degrees right now, Scott.
77. That's nice weather. Yeah.
It
That's
is
nice.
That
like
sounds like 6 in the morning
humidity
here.
is like 35%, and so the cautionary tale is we got to make sure we're drinking plenty of water, because at 35% humidity, you don't realize what, and so you don't start drinking enough water.
That's
And
right.
didn't
Right.
drink enough water. I drank a bunch of water last night, this morning, but
Mm-hmm.
boy, it's beautiful. It's beautiful here.
That's great. So tomorrow I'll be taking off for Albuquerque for the Astronomical League conference. It'll be the first time they've had one in a while. Although Nebraska Star Party, they've kind of trudged through COVID and still are having live events. So that's really cool. We expect to have a lot of really great speakers there. I hope to get with you live later from the field during that schedule. So I'll be publishing that schedule here pretty soon, and just announcing basically when we're going to have Astronomical League live, or Alcon live. From Albuquerque, and we'll keep you in touch as Explore Scientific is out there live from the road. So thanks for tuning in.
All right, Scott, talk to you.
All right. And we are here today to talk about the gravitational constant. Now, that sounds really kind of almost scary to me, Daniel, because I saw the math and I was just like, oh my God, this is going to be a deep dive today. But it really is important, I guess, that we
It
understand
is.
uh, the weakest force in the universe, which the four
Yes,
fundamental forces.
the weakest force in the universe.
Yeah, so we can understand. We can actually improve on orbits and mass and all the other things that gravity affects. But um, so I started to take a dive into it myself. It all starts with Isaac Newton, and then goes from there. But uh, you, it was a little tantalizing in your study guide about improvements upon the numbers, which have only made little tiny improvements since it was first really
Yes,
determined. So is that true?
that's true. Cavendish in 1798 figured out the constant of G to within about 1% of the modern value, but you realize we haven't made much improvement in the last 2 centuries. And there's some reasons for that. And we're going to dive
Cavendish
into it.
obviously got it right. So there you go.
He did. It was an astonishing accomplishment. But we
Mm-hmm.
want to go ahead and open the show with a couple of other things here. We like to do opening comments.
Sure.
10th anniversary or 10th birthday of Curiosity rover on Mars is coming up.
Woo!
Scott, I think it's like
All right.
August 5th.
10 years?
Today.
Really? Man.
Yes, 10 years, which makes me feel old. I'm like, wait, that was the last week, wasn't it? But something interesting cropped up in my newsfeed. NASA, the engineers being clever and fun-loving folks, they programmed Curiosity on its first anniversary on Mars to sing Happy Birthday to itself. It played the Happy Birthday song. But
cute.
People noticed two things. They said, one, who should ever have to sing Happy Birthday to themselves? That's sad.
Well, I did one time.
Thing,
it was very lonely.
Oh, yeah, I have to. I have to.
Happy birthday.
That makes us nerds.
Pouring down.
I don't know, maybe. But the other thing is that since that first birthday, because of power requirements, Curiosity hasn't had a birthday celebration since. It hasn't heard the birthday song since.
Well, who else is on Mars to actually sing Happy Birthday to
That's
it?
right. But that becomes incumbent upon us to sing for Curiosity. And the company Husqvarna, which I believe is Swedish, and they make garden equipment. And they market this lovely, awesome, Mad Max looking robotic lawnmower. It's like a Roomba for your lawn. And these things look crazy cool. No, it's a lawn cutting robot. But what they did is they issued an over-the-air software update. So on August 5th, all the Husqvarna lawnmower robots will play the Happy Birthday song for Curiosity.
What? Is that true?
Isn't that awesome? It's kind of like, I don't know if I'm supposed to be thrilled or if I feel like Skynet is imminent and the AI takeover is about to happen. I don't know. But it was just, there's a video link. There's a link to the article and a video in the show notes. And the video was so adorable. Oh my, it was so cool. And we contrast that with other robot news. In Moscow, just yesterday, I guess, they had a chess playing robot, which played 4 people at once and had a little robotic arm, and it would reach out and grab the chess pieces and move them. Well, one of the people playing it was a 7-year-old boy, and apparently he didn't wait long enough, and the robot is like, it reached out, grabbed his hand, and broke the kid's finger.
Wow.
So robot good, robot cute, robot bad, robot evil. Broke his finger. Yeah. So, and I must admit, I've been intrigued. I'm like, ooh, a robotic chessboard. That would be fun. And I'm like,
Yeah, if it loses and gets angry, is it going to like crush your hand or what?
Yeah, maybe. Let the Wookiee win.
Wow.
Anyway, the other cool thing that I came up in my newsfeed, and this isn't on it isn't on the downloadable show notes, but you can search for it and find it. There's a new NASA plan. This is a speculative plan, y'all. They would like to detect life on alien worlds by using our sun as a gravitational lens. Catch, in order to do this, you've got to get between 100 and 500 AU away.
Oh, yeah.
And you realize the Voyagers haven't got that far in, 50 years? And so what they're looking at is, how do you get it to go faster? Well, you have a deep dive at the sun. So you're talking about at least 4 CubeSats, which will dive in and go much closer to the sun than the Parker Solar Probe, and they will hit incredibly high speeds so that in about 20 years, they'll be able to reach this point. And what they'll do is they will assemble into a telescope that can use the sun as a gravitational lens, with the idea that we can view an exoplanet. Here's the catch. For each exoplanet, you have to be in a particular unique place to use the sun as a gravitational lens. So choose wisely. They're going to have to, this mission comes to life, they're going to have to do some research and pick the planet or system that they want, and then send their some assembly required robotic telescope out into deep space, farther than any spacecraft has gone before, reassemble itself, and then they'll go ahead and use the sun as a solar gravitational lens, which is just amazing and awesome.
Well, if they can get Jay West up there with all its hundreds of single point failure, I think it was like 344 and change or whatever single point failures on that spacecraft, and for it to work flawlessly, okay, I would say that NASA's batting 1,000. Well, so at this point,
at 100 AU away, you're not going to need a solar shield. So that's one nice thing that we can throw away. So those are two cool things.
Yeah. Daniel, I mean, we talked about kind of the care, the affection that maybe a robot could have for another robot, but there are people that are falling in love with robots, I guess, so I don't know what the world's coming to, but they cite that it will never betray you or whatever. Well, that's what they say,
Tell it to Will Smith.
Yeah, that's right. Do not make your robot jealous. Okay.
That's right. Do not make your robot lover jealous. Oh my gosh.
Anyway, there'll be more than hell to pay. Yes.
Also want to let people know, yes, it's our book, Star Mentor. And the first reviews are coming out on Amazon. And Mike Wiesner was very kind, put up a review on his website and on Amazon. And I would encourage you, please, if you're getting the book, I want to see a review from you, because feedback is so important for any author or producer of content. So I hope you folks will post a review. We also have 2 winners from our show that I don't have an address for y'all yet. Mike Wiesner was one of our winners, and he already has his book.
Yes.
And we need the addresses for our other 2 winners. And so, folks, if you reach out to me directly at astronomyforeducators@gmail.com, let me know you were a winner. We have your names, of course, and send me your mailing address so we can get your books to you. And you've got a signed copy coming. We've also been getting some more viewer questions emailed to me at Astronomy for Educators, and we've got a nice one from our viewer Pekala, good friend, and we're going to take that one at the end of the show when we usually do questions and comments. But folks, I love your questions and comments, so you're welcome. I don't know if you're like me, I usually had a brilliant question pop into my head 5 minutes after the conversation is over. That's just the way I roll. But if that's you, if you go, ooh, I should have asked about this, go ahead and email me that question at astronomyforeducators@gmail.com, and we will tackle your questions on the next show. So let's talk about finding G. And I considered various titles for the show this week. The story of G, finding G. Uh, but I just went with a simple title. And
You could have gone with Gee
not
Whiz. It could have been
Gee
Gee
Whiz.
Whiz.
That would have been a great. Where were you when I was struggling for titles, Scott? That would have been a great title. There's actually, if you think about it, and there's a brilliant book by physicist John Barrow about the constants of the universe. There are only 6 constants, physical constants in the universe that basically control everything. And these 6 constants, if any of them were different by a tiny, tiny fraction of an amount, our universe would not exist as it is. Life would probably not be possible. And Barrow's books on the mysterious constants is really a good read and highly recommended. And I'll see about putting that up in chat notes later so you can find that book if you're interested. But we're going to talk about the teeniest, tiniest constant of ever, which is Newton's universal gravitational constant. And I did this experiment. I do this experiment for kids all the time. And I should have a magnet here. I don't have a magnet handy. But what I would do is I would take a magnet and I would go, oh, look, you can pick up a paper click. And kids would go, yeah, big deal. In my physics class, in my astronomy class. And I, well, think about this a minute. If you take a refrigerator magnet and pick up a paper clip, do you realize your little fridge magnet is overcoming the gravitational field force of an entire planet?
Yeah, that's pretty amazing.
It is amazing. We're sitting here on the surface of the Earth. So we're literally at the strongest point of Earth's gravitational field that there is at the surface of the Earth. And a little fridge magnet can overcome the magnetic or the gravitational pull of the Earth. G is incredibly weak. It is the weakest force in the universe, but it has 2 overwhelmingly powerful traits. It never goes away, right? There's no way to, you can extinguish a magnetic force or an electric charge, but you can't extinguish gravity. There is no known way to null gravity. And the other thing, gravity's reach is forever. There is no range limitation on gravitational force. And because gravity reaches out infinitely and it never dies, gravity wins in the end. When a star dies, gravity wins. When a galaxy dies, gravity wins. And gravity always wins. So this mysterious gravitational constant we use as the symbol of G. And I'm going to go ahead and share a screen here. Oops, let's see. There you go.
You want me
Thank
to put it up for you, Dr. Barth?
Yes, please. If you would, that's so helpful. So at the top, and golly, Scott said, "Oh my God, the math we're gonna." And I'm like, no, don't be afraid of the math. Just think of it as a picture. Think of it as a picture. And if you look at that top equation there, this is Newton's universal law of gravitation, and it says to you, oh, the gravitational force between 2 things is the product of their masses, m1 times m2, divided by the square of the distance between them, and then multiplied by this constant called G. So what I did in the middle of the panel there, is I put these 2 things in boxes. And I said, okay, this is like A equals B times C. And all we're doing is rearranging to solve for G. And we see G here is the force divided by the product of the masses over the square of the distance. And what it amounts to is, if you think about gravitational force, the entire Earth pulls on you or I with a force of a few hundred newtons. It's just for an entire planet. Think about things that are powerful. You know, a stick of dynamite, a construction crane, and you realize, oh, it doesn't take that much to overcome the gravitational force of an entire planet to lift something. I can lift things. I can take my mouse and I can go, ooh, I'm lifting it. And I'm pulling up against the gravitational force of an entire planet. And so Newton actually implies this, but he never quantified it. He never gave it a symbol. He never gave it a name. He just implies that it's there. And we look at this and we go, ooh, well, why is this so special? And why is finding G so strange? Well, in nature, there are discovered constants, and then there are calculated constants. The speed of light, that's a calculated constant. The speed of light shows up as a term in Maxwell's equations for electromagnetics. And you look at C and you can rearrange the terms in Maxwell's equation. You can calculate a theoretical speed of light. When you calculate this speed of light, you can say, ooh, I'm going to be measuring something. It should be about this much. It helps a lot if you know the size of the thing you're looking for. If you're going and fishing for trout, you know about how big trout are. You know what kind of a line you need, what kind of a hook you need, and you know what kind of a net you need. And you know, oh, I'm not going to need a winch and a cable that would lift a whale because it's a trout. It's this big. Well, this is a calculated constant, and a lot of things are calculated constants. You can also say, oh, my theory predicts this constant should be this big, and then if you measure it, how close your measurement comes to theory is a test of the theory, right? If your theory is good, then nature's value in an experiment should be identical to your value from your calculation. And so calculated constants have no intrinsic limit for accuracy. And I put up there in the show notes, and I looked this up because this is something that's evolved over the years in my lifetime. How many digits do we know pi? And there are ways you can calculate pi. And somebody set the world record with 62.8 trillion digits of pi, which is, I find
60.8 trillion?
Trillion.
Man.
Trillion. And I was like, I need to go and print out 100 zeros on a page and measure it and then figure out how long a line. But I'm like, no, it's just ridiculous. It would probably stretch from here to Mars. It's a crazy big number.
Can we just round it off? I mean,
well, yeah, 3.14.
Okay, all right, that's good enough for me.
3.14159. That's as much as I know, and it's always been sufficient for my physics and astronomy classes. And you go, okay. And Guinness gave them a record. And the thing that occurred to me when they finally had a record, I'm like, you know what, Scott?
Okay.
Who checked their math? Who checked?
Who checked it? Oops, you missed one. You missed one right here, right?
Oh, wait.
Right at
13 trillion zeros should have been a 1.
Yeah, that's right.
Oh my gosh. So that's a calculated constant, and those are fun.
Man.
Then we get to discovered constants. Discovered constants are things that are true about the universe, but they don't come out of any theory. We simply measure them. We find out in our theory that we need them, but there's no indication from our theory how big or small they should be. And if we compare the 62, let's just round off, 60 trillion digits of pi, which just breaks my brain. G isn't known to more than 5 or 6 digits. We know it really precisely to 3 digits, and there are people who will say, oh yeah, I can give you G to 5 or 6 digits, but beyond that, it's guesswork. And you're like, wait. MIT, NASA, Cambridge, the ESA, NASA can't measure G to better than 5 digits? What's going on? Why is this so hard? Well, let's take a little bit and look at the story of G and see why. As we said, Newton is the first one who kind of implied that G was there, but he never tried to measure it. He realized it was beyond his scope, and he never put a value on it. And he had this lovely idea that, oh, if I could take a pendulum and put it next to a big hill. And Paul, I think we've got another image there for our audience. That's it. And Newton's idea was he would go ahead and put this pendulum next to a big hill being a very large mass of rock. And Newton realized there should be some force of gravity between the rocks in the hill and the pendulum bob. And think of it as putting a magnet on one side of an iron pendulum. When it comes toward the magnet, it's going to act differently approaching than it is receding. And so Newton said, oh, if we could put up a pendulum and isolate it and make it swing perfectly nicely, then the idea is, oh, swinging toward the hill, it should be different from swinging away from the hill. And he never tried this. And he realized there was a couple of difficulties. One, you have to have a really nicely isolated pendulum. And in the 1670s and 80s, that just wasn't happening for him. And in Newton's day, the ability to measure, 10,000, 100,000, millionths of a meter just wasn't there.
That wasn't going to happen.
Just was
right?
not there. And so Newton never really tried this. But some years after Newton's time, 1740, there were a couple of scientists. These are French fellows, and I'm going to massacre their names with my typical savoir-faire. Bouguer and Condamine. And I'm sorry, folks, if you are a French-speaking member of our audience, please
How
forgive
dare
me.
you?
Monsieur Bouguer and Monsieur Condamine. Anyway, they tried this in 1740. They went on a journey to Central America. I believe it was to Peru. And what they did is they actually climbed a mountain. They figured, if they could get farther away from the surface of the Earth, they could measure a pendulum and it would be in a different point in Earth's gravitational field, so it should swing differently. And that's true. If we look at the equation for the way a pendulum swings, it incorporates little g, which is the gravitational acceleration of the Earth. Physics fans and astronomy fans may know little g, how fast do you accelerate if you fall on Earth? 9.81 meters per second squared. And the farther you get away from Earth, the smaller that g gets, which is why we have microgravity up in the space station and in orbital platforms and things like that. We have microgravity because you're farther away from the Earth and you're free falling in orbit. So they tried to measure the difference in the swinging of a pendulum at the bottom of the top of the mountain, which was their version of Newton's experiment. It didn't work for them. They were able to refute the hollow Earth theory, because by measuring the change, if the Earth in fact was a thin shell, then gravity would change differently as you move away from the surface of the Earth than if the Earth is a solid body. And so in 1740, these two brilliant Frenchmen were able to refute the hollow Earth theory. And we've talked before, Scott, Karl Popper's idea that science
I read that even Edmund Halley was a proponent of the hollow Earth, right?
Edmund Halley and the hollow Earth, no good story goes away. And people have asked me, well, why do people believe these crazy non-science theories as opposed to perfectly good science theories, things like flat Earth, hollow Earth, da-da-da-da-da-da-da. And I've thought about this deeply, and I really believe that the stories, the theories, the false theories, the pseudoscience that gets believed, it gets believed and it sticks around for two reasons. One is that where science demands something of you. If you want to understand Newton's gravitation, if you want to understand relativity, if you want to understand astronomy, if you want to understand chemistry, it requires something of you. You have to spend time, energy, study. You have to work to master these ideas and come to grips with them. On the other hand, these very simplistic pseudoscientific theories, they make you feel smart. Oh, it's this way? Well, that's easy. And they make you feel special. Oh, here's what they don't want you to know. The Earth is really hollow. No, it's not. Just for the record. But these pseudo theories make you feel clever, make you feel part of a special elite group. Whereas science, sometimes people struggle and fail to understand it. That doesn't make you feel smart. And so I think kind of like mac and cheese, pseudo theories are easy to digest and they make you feel good. And so people tend to believe them. But these two French guys said, no, we can disprove that. So we take a look at this and we go, wow. So why couldn't Newton measure G? Why couldn't our pair of intrepid French scientists measure G? Well, G is unimaginably tiny. This is part of the stories like this are part of the reason I do the million, billion, trillion activity with people, to get them used to the idea of very large and very small numbers. G is by far the weakest force in nature. And we talk about the constants. You talked in the introduction you put on the Explore Live, and gravitational force is something like 38 magnitudes weaker than the electrostatic force. And we talk about just the constants. The electrostatic force constant, sometimes called Coulomb's constant, is 20 orders of magnitude larger than G. And you go, gee, 20 orders of magnitude, 100 quadrillion times. I have on my desktop here because I picked up my data, and you should too. I have, probably lots of us have these. This is a portable hard drive. Right? It's
sure.
This is a terabyte hard drive. Tera. So it has 1 trillion bytes of storage. My little flash drives that I record my show notes and things on, those have about 16 gigabytes. And this little hard drive is so many times bigger, and yet it's a drop in the ocean. 100 quadrillion is something like 100,000 trillion, which just breaks my brain. And we've done this before, but for those of you who didn't see the show, you can put it in $100 bills. $1 million will fit in a backpack or a rucksack you take your clothes to the gym in. $1 billion in $100 bills is a 2.5 meter by 2.5 meter by 2.5 meter solid cube of money that weighs 10 metric tons. $1 billion is a cube 8.5 by 8.5 by 8.5 feet. It would take 11 one-ton pickups to haul it away. If you lit it on fire, it would burn for a month. $1 trillion is a soccer field, end zone to end zone. I suppose we could say football field and be inclusive for both Europeans and Americans, right? They're both about the same size surface. A football field, end zone to end zone, sideline to sideline, 2.5 meters deep, so 8.5 feet deep, of neatly stacked $100 bills. And this comparison between the electromagnetic force constant and G is 100,000 trillion. How big is
100,000 trillion?
100,000 trillion. And I didn't go ahead and I know. A soccer field is something like 2.5 acres. So you're talking, and that would be bigger than Arkansas. It's approaching the size of Germany or Texas. It's an insane, all stacked 2.5 meters deep with neatly stacked $100 bills. It's just the difference between the two is just insane. Where we can easily measure the electrostatic force constant, we've done this. Many of you probably remember back in school where you did this, where you had two little pith balls and you charged one of them with static electricity and they either attracted together or they swung apart as they hung on their little pieces of string. I'm sure many of us have done this little clever experiment, and it's fun.
Sure.
And you can do this in a classroom with a couple of dollars worth of materials. It's really simple and easy. But measuring G, because it's 100,000 trillion times weaker, is very challenging to measure something so small. So, wow, this just kind of hurts my head. And I had somebody ask, and this was just a casual conversation, and he said,
Sure.
well, if it's so tiny, well, what if it was bigger? If it was bigger, that would be bad. G gives us our force of gravity. So imagine we just add 2 zeros onto G, right? We make it 100 times larger. Stars would compact so hard that even small amounts of dust and gas would form stars. They would burn so hot and so fast, they would all go off like firecrackers. Even the biggest stars would last maybe a few hundred or maybe 1,000 years, and then they would explode and die. Life can't evolve on those timescales.
No.
Stars would burn out before their planets could form. It takes 500 million years to form the planets in the solar system. And if the star goes kapow before planets form, it would be a lifeless universe. Life would be impossible. Everything would end up in black holes, and pretty darn quickly. It would be atrocious. If G were smaller by just a fraction, fusion wouldn't be possible at all. It wouldn't be possible to get enough stellar material in one place to have a core compacted hot enough to cause fusion. So the universe would be forever cold and dark. Planets would form, but there would be no life because there would be no energy source to drive the formation of biomolecules or biological evolution. So G is really finely tuned. If you really want to get into a deep dive on this, friends,
really important.
This is the Anthropic Cosmological Principle by John Barrow and Frank Tipler. And these two fellows argue that, in fact, the universe is well tuned for life. In other words, if the universe were very significantly other than it is, we wouldn't be here. And they say, well, this doesn't necessarily mean that there's a creator tweaking the scales, but maybe every time the universe goes crunch bang with a new Big Bang, maybe the constants of nature reset. We're here because this time we won the jackpot. All the constants were amenable for the formation of stars, planets, life, and maybe on another roll of the dice, so to speak, the cosmic dice, there might have been many universe creation destruction cycles which were lifeless. That is something that will keep you up nice. Barrow and Tipler, and great book, lots of fun. So let's talk about the first fellow to actually measure G. And I think we have an image there. If Paul will throw it up for us. There it is. And this is a nice image. And I think, Scott, on the Explore Alliance site, if you go there and you look up the description, you found actually some kind of a drawing of Cavendish's actual experiment, I think.
Yeah, that was kind of cool. Mm-hmm.
Yeah. Basically what Cavendish did, if you take a look at the dark green balls hanging on a wire, he took 2 masses, put them on a rod, hung it from a thin wire, and he let the masses get stable, and he glued a mirror to the wire.
Okay.
Well, what's all this about? His idea was really brilliant. If he can get these balls to be deflected by gravitational force, the movement's going to be very small. Well, how do I magnify that enough to see it? His idea was, we'll take a very thin slit of light. He did not have lasers at that time. He would have used collimating slits, but he has a very thin slit of light. This slit of light, this beam of light falls on the mirror. And then if the mirror tilts slightly, the direction of the beam changes. Well, you can put a scale on the wall as far back as you can. And so now his measuring arm on his dial, so to speak, can be many meters long and extremely precise.
Hmm.
And that's what the mirror was for. And once these balls, and they were on a bar hanging from a wire, they were inside an enclosure. And once they were all stabilized and not moving, then he raised up two very large, and I don't know if they were iron or lead, two very large, massive metal balls, and wanted to see if indeed gravitationally the two masses would be attracted. The very large masses were fixed, they could not move, which meant that the smaller masses, the smaller balls, would be attracted to them. And this wire would work as a torsion spring, like on a watch, and they would twist a little bit until the forces balanced, and Cavendish could measure the deflection of the light beam, and from that he calculates G. And he comes up with a value of 6.74 times 10 to the negative 11th. So a decimal point, 10 zeros, followed by 674. A decimal point followed by 10 zeros. So what? 10th, 100th, thousandth, and so on it goes. 10 zeros. Yeah. 12 is a trillionth, so you're talking about 100 millionth is the order here. And the units are kind of strange. Meters cubed over kilograms second squared. Don't worry about the units at all. The units don't matter. Basically, what is G? G gives you a little multiplier so that when you have gravitational force on one side and this inverse square product of the masses over the square of the distance on the other side, G is the multiplier that makes the two things equal to each other. So it's a proportionality constant. And you can think of this a lot of ways. Yeah, I can say, oh, well, it takes 7 lasagna noodles to make 1 pound of lasagna in my kitchen. So I think, ooh, if I wanted to make 3 pounds of lasagna, I would need 21 lasagna noodles. And it's a simple multiplication. What's the proportion there? Well, 7 noodles to 1 pound of lasagna is just a proportion constant. If anytime any of us have ever scaled up a recipe, oh, can we all come to your house? Will you make tacos? Yes, sure. I usually make a pound of taco meat. I realize, and I do this every fall, all my astronomy students come to my house for taco dinner. And I realize I'm going to need 6 or 7 pounds of taco meat. So I scale my recipe up with a proportionality constant. I just multiply my ingredients by the number of servings I need, and it all comes out right. So all G is, if any of you have scaled a recipe up in cooking and just multiplied by how many servings you need, that's a proportionality constant. That's exactly what G is. So mathematically, Scott, it's not tricky or mysterious. It's something we all have a comfortable working relationship with as adults.
Right.
Because we proportion things all the time. It's just that the proportion for G is really, really small. And when you take the mass of 2 planets multiplied together, divided by the distance, you get a quite large number. And the gravitational force is really weak, so you multiply by this very tiny number, which is G. Well, the crazy, stupid thing about it, 1798, what, 224 years ago? There's been no real tremendous improvement on the measurement of G since Cavendish did it. And furthermore, virtually everyone has used some variation of his method. And this is
Aren't there any new methods? I mean, were there other ways to do this?
People at ETH in Switzerland.
Yeah.
And don't ask me what ETH stands for.
Event? Is it the Event Horizon Telescope?
No, it is not. This is their MIT. This is their, you're right. It's the Ecole Technique something, and I'm butchering the language, I know. But this is their MIT, this is their Cambridge. That's the institution where Einstein went to school. ETH, and got his physics degree. And it is their premier physics research institute in Switzerland. And the professor, Jörg Dual, basically came up with a new method. And what Professor Dual realized, all of the measurements for G so far have been static. And what we mean by that is the static methods means we measure G in the Earth's gravitational field. Now, there's a real good reason for this. It's really difficult and expensive to get away from here. It's really expensive and difficult to get away from here. I suppose the astronauts could have taken a Cavendish-style experiment to the moon, but they did not. They were kind of limited on space, and so they did not. It'll probably be done one day, and we might be able to do it somewhere out in space, but nobody's done that either. But the problem with measuring in a static gravitational field is that everything affects it. This is exactly the problem that Adams and Leverrier were struggling with finding the position of Neptune. Because they realized if something is screwing around with the orbit of Uranus, well, Saturn would pull on it, Jupiter would pull on it, the sun would pull on it, the little planets in the inner solar system would pull on it. You have to account for all these things. And if you're measuring G, we know when we watch the tides. The sun and the moon both strongly affect tides on Earth. So guess what? When we measure G in a static field, we need to know where's the moon, what's the phase, where's the sun, how are these fields interacting, where's Venus, where's Mars. Jupiter probably affects it significantly, and it gets crazy complex because we're measuring Earth's static field. And so Professor Dual at ETH in Switzerland comes up with a brilliant idea. I'm going to use a dynamic method. I'm going to use gravity waves, which is just, I looked at this and I said, this is brilliant. And what he did, and I looked at this and I immediately knew. I knew where his inspiration for this experiment had come from. Just to give you the idea, you look at the green bar and the blue bar. These are metal bars about a meter long. I've seen pictures. I've read his paper and I've seen pictures of his experiment. These are bars about a meter long. And the first one, the green one, is set in motion. It's set in motion vibrating. And it vibrates. What it's doing is creating gravitational waves. And it's isolated in a box. It's in a vacuum. It's all isolated, so it can't be a sound wave effect. And the gravitational waves spread out at the speed of light. And eventually, those gravitational waves cause the blue bar to start resonating. Again, high school physics class. Some of you may have seen this resonant experiment. You have a little wooden box with a tuning fork in it, and you have two of them. And you strike one, and the tuning fork in the other begins to vibrate sympathetically. You can do this with two pendulums attached to the same bar. You start one swinging, and the one next to it will begin swinging. And this sympathetic vibration, anytime you've driven by or you've had someone drive by with usually the tiny little cars with the great big stereo, right? And you can watch their windows vibrating. And in your car, several meters away, you can feel your kidneys vibrating.
Yeah, you can feel it. Yeah.
Right? And
in
they're
your
like,
chest.
My music's so good. Everyone needs to hear this. Okay. Well, this sympathetic vibration thing that happens, it happens with gravity waves too. That, after all, is the whole principle behind the LIGO experiment. Gravitational waves come in. There are two laser beams at right angles, and space gets expanded and contracted, and this is how we detect gravity waves. Well, not only did Professor Joule at ETH, not only did he detect gravity waves, he's using gravity waves between two bars of known masses to calculate G. The reason this is brilliant, Scott, that unlike static methods in the Earth's gravitational field, the Earth's gravitational field is affected by everything around it. On the other hand, these gravitational waves that propagate from this vibrating bar are not affected by the Earth's gravitational field. They're not affected by the sun, or the moon, or Jupiter. And the reason that is, these waves are at a very particular frequency. And so if we only look for results at this frequency, the Earth isn't vibrating like that. The moon isn't. Jupiter isn't. None of them are producing waves on the right frequency to cause the other bar to vibrate.
So all these people that claim that crystals give them a certain vibration, I guess on some level...
There was a Beach Boys song, wasn't there?
Yeah, good vibrations, right?
Vibrations? That's right. Don't ask me to sing that, you'll be disappointed in the result. But yes, and there are people who say, ooh, crystals give me vibrations. On the other hand, this, of course, has been tested by helpful scientists. Let's see if we can measure a vibration. Nobody's ever been able to measure this. And, you know, if it makes you feel good and there's a significant psychological, behavioral, emotional effect, good for you. Terrific.
Why not?
Enjoy that. But it's beyond the reach of my science, which doesn't mean it's not real. It means I can't measure it.
I like
so
that
when they
term,
talk
beyond
about
the reach of
vibrations,
my science.
I'm not gonna say throw your happy quartz crystal away. Don't do that. If it makes you happy, by all means. I'm just going to say that's beyond my science, and there are lots of things that are beyond science. And science continues to find new things that are not beyond it. Gravitational waves were a fantastic idea that very few people believed in. And maybe we'll do a whole program on those. I'm reading a wonderful book on that right now. But these waves let people detect, and because of these advantages, and no thing could vibrate that way except the bar, they were able to isolate these two bars in one system and measure the results. And people are going to ask, oh, so they got a better measure of G? No, they did not. They got a measure of G within about 2.2% of the accepted value. So their error was twice as big, more than twice as big as Cavendish. And their uncertainty is way too high. Sorry?
Yeah, twice as big as Cavendish's.
And unlike Cavendish, in science, we talk about what's the uncertainty, and this is often expressed in terms of what we call error bars. Here's a point, and here's little bars coming away, which says, here's this data point, and here's how well we know this. Here's how accurate our experiment was. We got this value. How much error is in there? In other words, if we did it 10 times, what's the spread over which we would expect to see results? Their uncertainty is too high. They just came right out and said it. Our uncertainty is too big. This is not a reliable methodology yet. But what they really did, two things. They said, oh, they are, as far as I know, they are the first people to produce gravitational waves and use them in a scientifically useful way.
Oh, well, that's cool.
That's awesome.
Yeah.
Remember J.J. Thomson, who got the Nobel Prize in 1906 for the discovery of the electron. And at the dinner, the celebratory dinner, he offered a toast and he said, here's to the electron. May it never be of use to anyone. because J.J. Thomson was all about pure research. Science should be science for science sake.
Right. Yeah,
And
that's right.
all these people who want to make science the handmaiden of business and industry, bah humbug. We should pursue knowledge for its own sake, which I'm all for that, but I don't see not using something if you find it's useful.
That's right. But who's going to build the buildings, right?
Who's going to build the building or the brakes for your Toyota, right? Who's going to build your electric car battery? We need scientists, we need theorists, we need engineers. They are the kind of three-legged stool upon which modern civilization success rests. Well, their uncertainty is too high, but you think about it, and I don't think they mentioned this in their paper. They are the very first people that I know of to produce gravitational waves and use them in a scientifically useful way.
Very cool.
As an engineer would to produce an effect, right? We understand about friction, and we know when our pads clamp our brakes, we slow down, and we use that idea of friction in a useful, controlled, predictable way in a device to produce a desired result. They are the first people to master the use. They are the Marconi of gravitational waves, right? People knew about electromagnetic waves for a long time. Radio waves. Marconi's the first one who said, oh, wait, I know how we can use that. We can make a transmitter for signals. Wow.
That's right.
And they are the Marconi. They are the Wright brothers. The Professor Duell and his team are just, I think there should be a Nobel in their future just for that. But I'm not on the committee. You know, Nobel people, if there's a vacancy, call my publicist and see. No,
Daniel, we have some good questions and comments.
Good.
Okay, that should dive into here. So let's see. Let me move over so that I'm actually on camera here. Okay. Let's see. We've got quite a few people commenting in today. We got Mike Wiesner, Norm Hughes, Pekka Hautala, Harold Locke. Let's see. Who else? Charity Rose Walker is chiming in today. Lots of back and forth chatter, good questions. I'm going to get to that in a second. Lots of back and forth chatter. All right, that looks like our group, at least on YouTube. I'm not seeing the other chats coming in, but I do see the YouTube chat. And so let's get down. So what did NASA learn of this? Send an MP3 player with a rover and have its own battery and play the song to a rover? You know, so that's...
they put some kind of speaker on it.
Right.
And do you remember the old Commodore and Apple computers that had the little tiny, 2-inch speaker
little
inside, Scott?
Speaker. Yeah. Yes.
Teeny speaker. And you could program values and get it to play songs. That's basically what they did. And they put the code for Happy Birthday in there. It amounted to a very small amount of memory, a very small amount of power, and a very small amount of weight. And it was let's be nice and call it a proof of concept rather than a prank. It's kind of a proof of concept as opposed to a publicity stunt. And a rover sang Happy Birthday to itself. And cool. That was really fun. But of course, as it's kind of if a tree falls in the forest and no one's there to hear it, does it make a noise? Does the rover make a noise if no one else is there to hear? I say yes. Mars was there to hear. The atmosphere transmitted the sound, so I say yes. And that's what they did. And the Husqvarna robots, the lawn mowing robots are all going to sing. Something like 100,000 Husqvarna lawnmower robots are going to sing Happy Birthday on August 5th, which I think is brilliant. And I would encourage our listeners, if you have one of these devices, by all means, post a video on YouTube. I want to see it singing happy birthday in your yard. They're pricey robots. They're not like a Roomba. These are in the $1,800 to $2,500 range, depending on how big a yard you've got. And
Right.
none of them would do my lawn here at the ranch. So we have about 6 acres we mow and care for, and none of those robots would do that. We also have a question, Scott. Okay, go ahead. We had a question that came in from Pekka via email, and he was asking about where photons come from. And I'm going to give you the 25-cent answer here, Pekka, and this might be a topic for a whole nother show. Basically, photons are nature's way for atoms to shed energy. If atoms get too much energy, they're heated up, they're struck with a gamma ray or an ultraviolet ray, and they get a lot of energy. What tends to happen, that energy shows up not in the nucleus, but in the shell of electrons. The electrons get boosted up to a higher level, and then after an indeterminate period of time, they collapse. And the amount of energy between the high level and the low level, that's the precise amount of energy carried away from the photon. And the energy of the photon controls its frequency and its color. So you need things that are really hot to give off X-rays and gamma rays. They have to be tens of millions centigrade to give off that kind of energy. On the other hand, radio waves, infrared, those are small amounts of energy. And this is the story of quantum and Einstein's discovery of the photoelectric effect, for which he got his Nobel Prize. And so, you know what, Pekka, I'm going to do a whole program for you on Einstein, the photoelectric effect, the birth of the quantum theory, which Einstein spent the rest of his career fighting against and saying, no, it can't be true. And how we get photons of different frequencies.
I'm going to look forward to the photon show. I had a physicist from Caltech about a month ago explain to me, because we were talking about the speed of light, okay? We were talking about the speed of light, and the way I understand it is a photon can be created in the fusion process of a star, and photon can be captured for a long time, and then it can, at 186,000 miles a second, travel across space and land into your retina, okay? But he was saying that's not very accurate, okay? Really. And he said that spontaneously, although there is light travel speed, at the time that the photon is created in the star and the time that you see it in your eye, I don't know. I've got it. Maybe I'm sure I had misunderstood this, but what I got out of it is it happens simultaneously, like entanglement. Okay. So I don't know. This is a former Caltech professor. Okay. Explaining this to me. So
I'm not going to disrespect that idea, but I'm going to ask my good friend Dan Kennefic.
I said, is it going 186,000 miles a second? He says, yes, it's been measured. And I said, I'm
going to ask my pal, Dr. Kennefic at the U of A, about this. He is a physicist. He's written books on gravitational waves, and he's an historian of science. And his book.
I need to know this because I need the 30-second elevator version explanation of this. Okay.
I'm gonna track Dan Kennefic down and I'm gonna buttonhole him and ask him this.
Okay.
That's not the way I understand it. I do know that there's a latency period between the time when a photon is created in the core of a star and it escapes from the photosphere into space over 100,000 years.
That's
Over
that's my
100,000
experience,
years.
or not my experience,
And,
but what I know of it, or thought I knew.
and basically, when we talk about that, we realize that, the photons are basically handed off. One atom emits it, the next one absorbs it, and it gets re-emitted in a random direction. And the time it takes to cover that 500,000 mile, 1.5 kilometer distance is extremely long. But once it's released from the photosphere, then it travels in a straight line until it strikes something. So I'm going to have to ask my pal about that.
Yeah, I mean, does it make like this pipe of?
Yeah, not the way I understand it.
I don't know. I don't know. So
Not the way I understand it at all. We got another question here. We know light
Okay.
is affected by gravity. What about sound? No, not really. Sound is a mechanical wave. So it basically is one particle colliding with another and making it vibrate. And to some extent, the particles are controlled by gravity, but the mechanical transfer of pressure is not. And I suppose you could say that a very big sound wave from a very big bomb or volcanic blast would travel around the curve of the Earth because gravity held atmosphere onto the surface, and so indirectly is, but in reality, no, there's no effect of gravity on sound because it's a different kind. Sound waves don't have mass, whereas photons do, and that's why they're affected by gravitation. Question: does the gravitational field vary along the land versus the sea? To an extent, it does, Charity. We have gravitometers, I believe is the right word. You can set them up and measure the gravitational field anywhere on Earth, and it depends on what's the composition of the material underneath you. So if you are in a very rocky area where the ground underneath you is mostly granite, like New York City is a granite island, and it's all very hard, dense rock, the gravitational field in New York would be stronger than, say, an area out at sea where the first couple of miles of material underneath you was water, which is about 60% the density of rock, something like that, or excuse me, about 1/3 the density of rock. Water has 1 gram per cubic centimeter. Rock has between 3 and 5. So, yes, being out at sea, there would be a lower gravitational acceleration. By the same token, if you go up to the top of a very tall building or on top of a very tall mountain, gravity is weaker. That's what our French scientists were trying to measure. And so, yes, and this kind of technology has been used. We measure with lasers the altitude of satellites orbiting Mars. And we have found by the changes in altitude caused by the changes in gravitational field as the orbiter flies over higher density and lower density regions, these scientists were able to discover subsurface oceans worth of water, whether that's solid, involved in hydrates, if it's liquid, we're not sure. But it's like, wow, there should be entire oceans of water underneath the poles. And they measured that with exactly the kind of effect you're talking about, because when you're flying over an ocean, whether it's subsurface or on the surface, you're flying over a lower density area. So gravitation is weaker, and the satellite would pop up a couple of meters with no thrusting. It's just gravity would be weaker. And so, yes, you can measure that. So no rock, no gravity, period. Less rock, less gravity. I wouldn't say no gravity, but yes, the density. Think of it this way. The density of material under your feet controls the strength of the gravitational field where you are. Although to measure this takes some really high precision equipment. You're not going to do this with a bathroom scale or a pendulum. You need some really high precision equipment. But yes, it's done. And lots of people use this technology. Geologists looking for oil and minerals, natural gas, archaeologists looking for fossil layers in rock. Lots of people use this. Exploring impact craters is often done with gravitometers. What about drag? You'll have to clarify that for me, because we're really talking about gravitational fields. Pekka says the light travels from sun's center in like 10 million years before
tens of millions of years before reaching the surface.
There's a well-known value here, Pekka, and we'll have to send all of our audience members to Google and find that number out.
That probably varies star by star, because of the size.
It would.
Right?
It's fairly well known, or we believe it's well known for our star. But yeah, I'm sure the size and density of a star would affect that.
Yeah, I've seen values for that range from a few hundreds of thousands of years to millions of years. So I think there's a lot of argument there. What about gravitational anomalies that they find on the moon, they find on Earth? Are these. Why wouldn't it all be the same?
NASA's word for this is MassCon. They like clever little nicknames for everything.
Okay,
mass concentration. And one of the stronger points of evidence for the big impact theory is that we find this large mass concentrations on the moon, indicating that there were very large impactors that slammed into the moon and became incorporated in it. The Aitken Basin at the moon's south pole, 2,500 kilometers wide, 12 kilometers deep. And
this is yesterday's ALPO, the Association of Lunar and Planetary Observers. They were talking about these mass cons. First time I'd really heard of the term myself, but I have known that there were gravitational differences.
Volcanologists use this, Scott, to track the movement of magma in magma chambers. Because as the magma surges towards the surface, gee, surprise, guess what? That's very high density rock, and it changes the gravitational constant on the surface. I know they've done these type of experiments in Yellowstone National Park, which is supposed to be a supervolcano site, and they've used gravitometers to measure, and they also use laser altimeters and seismic sensors. They use a whole suite of sensors, but they're measuring mass cons. A giant blob of lava moving towards the surface is a mass con, and it's moving. We've heard of these mass cons deep within the Earth's interior, which are affecting the magnetic field. This was in the news just this summer. And people are using this kind of technology, probing the way these giant mass concentration blobs shift and move. And they think this has linkage to the reversal of the magnetic field. Which there's a lot of Cox Springs which are ready to go off. The San Andreas Fault. Scott, have you not heard all your life that we're waiting for the big one on the San Andreas
the giant slip, the 10.0 magnitude. It's going to break California off into the ocean, and it becomes its own island.
The whole thing.
Yes.
And people have been talking about this for centuries. That the flip of the magnetic field, the course from the bottom of the ocean says this occurs every 250,000 years, and we've been 700,000 years since it last flipped. And why isn't it happening? It's like
it's overdue, right?
This is a rubber band, it's a snap, and it hasn't gone. Why not? And nobody's really quite sure. So
in the meantime, they keep building more houses in California, right? So
Of course we do.
Right
Of course
on
we
the
do.
fault line.
Well, and you've driven along Highway 1. You see these crazy
Yes.
houses built out over the cliff on stilts. And
Yes.
I look at these things, and as a scientist, I'm just like, oh, heck no.
Right. Pacific
You know,
Palisades, California, the Earth moves like
Yes.
a foot a year or something like that. I mean,
Foot a
a
year.
lot. And all
Yeah.
the water pipes and gas lines and electric are above ground. Because if they go
Yes.
underground, they break, right? So,
Right.
and the houses,
I
the
was-
multi-million-dollar homes are constantly being repaired, you know, so giant
I
cracks
was,
in the
and
wall.
I'll get Charity's question in a second here, but I will tell you, I was lucky enough
Okay.
to see a seismic wave. The Whittier earthquake, which would have been
wow.
1987, 7-pointer in California. I was teaching in Diamond Bar, California, which is a high school built on a hill. And the entire athletic field is filtered. I was outside with a physics class on the athletic field during the Whittier quake, and we saw the ripples in the soil rushing towards us about 30 inches, about
It looked like liquid, like liquid
75
ripples.
centimeters to a meter. It looked like a wave coming into the beach. And it was coming
That is
across the
wild.
ground, and I saw it knocking people down. People were just falling down. The waves were going, and it's like, this is nuts. An old Midwesterner like me, for those of you overseas, where I come from, Wisconsin, Arkansas, Illinois, we don't have earthquakes here. Tornadoes.
Well, we do
lightning,
now, but we
yeah,
do
but,
now because
you know,
of
we don't-
fracking.
you know,
Yeah.
it's not really earthquake country. Never experienced one till I moved to California, and it's such a disconnect. It just, your mind says, this can't be real. This has to be a science fiction film. And you're just
Sure.
seeing this wave come across the ground. Let's see. We had Charity's question. Does drag affect photons in the atmosphere? In a way, yes. We call it refractive index, Charity. And what actually happens is the speed of light in different materials is different. So when light passes from a vacuum, where it is the fastest, into an atmosphere, it slows down. And we use this. I'm using this effect right now with my glasses. We all use it with telescopes and binoculars. When light goes through a lens, the way it works is the light touching the lens slows down because the lens is curved. It takes the wavefront and it bends it. That's how light is focused. And we can do a whole show on that with ray diagrams and fun. So I will just tell you, it's not drag per se. It's called index of refraction. But yes, the speed of light changes in different materials. And every telescope, microscope, and lens maker uses that concept to produce lenses for eyeglasses, binoculars, telescopes, every kind of optic you can imagine. And we use that technology, that wave bending technology, in microwave ovens. So yes, we use this technology all the time. Acoustics are much the same. We're shaping and controlling waves. We build a concert hall to focus the sound energy from the band out towards the audience. Hollywood Bowl, Carnegie Hall. This is exactly, these people understand this science precisely. So yes, it's a science of waves. And you're very welcome. I'm glad the answer was helpful. So there we go. And Scott, I'm hoping that we've got lots of good questions. I know we're a little over time. Friends, if you have more questions.
But I think that there was, the conversations went, in many different directions, including to, a conversation about Tesla, which made me look up a thing about Tesla's mysterious box. Okay, so if you want to read something about the genius that was Tesla, he was also this might have been one of the reasons why they thought Tesla was crazy to a degree. He claimed to. You remember he claimed to invented like a death ray. Okay.
Yes.
And he to kind of maybe deflect he was facing a $400 hotel bill from the Governor Clinton Hotel in New York. And he offered, instead of paying the $400, he offered a working model of the weapon, okay, as collateral. He delivered that model in a locked case, okay, and cautioned that the box would explode if opened by an unauthorized person. I don't know how it would know if it was authorized or unauthorized, but people were intimidated because Tesla had done so many things that were just utterly amazing, right? So intimidated by
to clarify for our audience, Scott, we're talking about Nikola Tesla, not Elon Musk and the electric car company.
Not Elon Musk, that's right.
Came out and said, I have a death ray in a box that'll explode. It sounds exactly like him. Elon, we don't need.
All right, this is in the 1940s, by the way. Okay, so, but they put that because they were scared to death of this box. Okay, they put it into the hotel's safe. Okay, which again, if this thing is so dangerous, I don't know how the safe would protect anybody. But they did. They put it in the hotel vault. In 1943, Tesla was found dead in his hotel room. And so the FBI asked a guy named John Trump, okay, another Trump, to analyze his papers. They found nothing of value in Tesla's writing, okay? And so they turned their interest to the mysterious box in the vault. And after the disappointment of Tesla's papers, the possibility that a previously unknown death ray was hidden in the storage vault of the New York hotel was startling. Trump went to cut the brown paper wrapping from the mysterious box, and the FBI agents accompanying him withdrew from the vault. Okay. Automatically, the box contained, anticlimactically, the box contained a wooden chest with a brass hinge lid that held only a whetstone bridge. Now, I went to go search what a wheatstone bridge. Okay.
Wheatstone bridge.
A wheatstone bridge is an electrical circuit used to measure an unknown electrical resistance by balancing two legs of a bridge circuit.
Right.
One leg of which includes the unknown component.
High school physics experiment, the Wheatstone bridge.
So that was Nikola Tesla's thumbing his nose at the establishment, I guess. I don't know. But
I just have to think if they found nothing in his papers, it's because they didn't understand them. I can't believe
very possible.
Either that, or they were a set of.
We may find out that the Wheatstone bridge is the main component of the death ray in 200 years from now. I don't know
how that would work, but I'm not claiming to be Nikola Tesla brilliant. No, not by any stretch. One nice thing about doing this show, Scott, is it's very fortifying to one's humility, because you spend your days looking up things and that truly brilliant, revolutionarily intelligent people have done, and then you, in your own poor way, try to make them more accessible to more people. And that's a talent to be sure.
Right.
Science explainer is not popularized. It's a talent to be sure, but I in no way. I stand on the shoulder of giants, and no, it's not a dig at short people. When Newton said, "I stand upon the shoulders of giants," many people believe he was taking a dig at his longtime rival, Robert Hooke, who was very short, less than 5 feet tall. And Newton was always taking digs at him. But many people have said before, and matter of fact, Stephen Hawking's book On the Shoulders of Giants, where he edited the papers of major scientific breakthroughs. I stand on the shoulder of giants, and I'm just standing here shouting out what I have found so I can bring everybody else along. And really, I'm hoping this show gives people a start for their own research and ideas and exploration into ideas about astronomy and physics. Wow, a great show. I'm hoping, folks, if you have questions, email me directly, astronomyforeducators@gmail.com, and I will address your questions on the show. I love that we got questions from some new viewers today, people I haven't heard of before. Charity, welcome, and thrilled to have you asking questions. And everybody else, come on, y'all, jump in. So
That's right.
Well,
something that has to soak in. It's a lot to absorb, right? So
it is a lot to absorb. But there you go.
So I have a little, before we go, when we close out the show, I do have a little video, a featurette from the James West Space Telescope team. So I'll play that a couple of minutes, and then we will say goodnight. So here we go.
I came up with Elements of Web because I had seen in all of our articles and videos that we kept mentioning that we used gold and beryllium for these mirrors, that there are all these special materials, but we didn't really explain why we used them. So I wanted to get sort of into the nitty-gritty of the material science to explore why these were, and then actually just demonstrate why these materials behave the way that they do.
Not only was it I think, a cool science adventure for you because you did a lot of that research, it was an adventure just going out and capturing everything.
That's the great, beautiful Salt Lake back there. Okay, we just got attacked by, they're still swarming around us, these little gnats.
I will say that my proudest moment was being able to go to the beryllium mine. It took a lot of work to get to. You know, we found the beryllium shop, and then we got them to talk to their people, and then convincing those people to let us, you know, fly into Salt Lake City and actually go to the frickin' beryllium mine.
This has all been mined out, so that's the.
We've had like so much latitude in this project, which we're very lucky. But yeah, so we were able to hire a drone operator, which was so cool. And so he was able to get perspectives on this huge hole in the ground that we would never otherwise be able to see. And actually get like a really good perspective on like just how massive it is and really how much rock you have to remove to get even the smallest amounts of beryllium.
COVID just wiped this whole thing out because we were planning to go to a lot of different places. And then when COVID hit and we couldn't go anywhere, she did, I want to say like 80% of the whole production at your house.
Yeah.
And you did some amazing stuff at your house.
We're recording.
But first, I have to make some distilled water. It was fun. I mean, it made me take a little more time to think about what I was talking about, and I actually think they ultimately made a better video.
I already see two pieces.
One of the great things about this job is that you can, you meet a lot of different people, you learn a lot of stuff, but you're also able to go into places and see things that, nobody else gets to see. And I think the Elements series is really one of those projects that we were just able to go and into different places.
Sort of my philosophy on life is just start doing the things that you want to do. You're never going to have the gear that you want. You're never necessarily going to have the time that you want, but like try to figure it out and just do it.
What a lovely way to end the show. It's your coffee.
That's right. Star Mentor, get your copy now.
Get your copy, post your review. Absolutely. Well, this has been a hoot, Scott. I wondered if I would have enough material for a whole show here. I was prepared to stretch things out, but this went deep.
Gravity's a heavy subject to talk about, really. So, nah.
I'm not there in the room to beat you for that.
I gotta add the sound effect. Wah, wah.
And if you guys like this, please post comments, because, like I said, there are 6 essential constants of the universe. We only covered 1 today. So we could, sprinkle these in other shows. They've made good show topics. And if you like the show, if you enjoyed it, please leave us a comment. Please share with your friends. Please subscribe. And go find us on YouTube, Explore Alliance on Facebook and on the web. and Astronomy for Educators page on Facebook and YouTube. And we'll see you next week. And thanks for viewing.
Good night.